Yes, guys. Now, we are on to the last part. We've made it, right? We're on to the last part of the centers of masses bit of this chapter. So let's just get cracking with it. Now, here's an example. Let's have a look at this. So in the following diagram, we've got a non-uniform beam again, CD, right? So C and D. It's got a weight of 60 newtons and length of 4 meters. So we can fill this whole length in as 4 meters. And it's resting on two supports at E and F. So we've got E here, we've got F here. So fill those in. Get your reaction forces into there as well. Look, RE and RF over there. And they told us C to E is 1 meter. So there we go. That's 1 meter over there. C to F is 2.5 meters. So again, let's be clever about that. And what we can do is say this is just 1.5 meters. Okay, fantastic. Now while we're there, wait, this is 1, this is 1.5. That's 2.5. So that means this on the end must be another 1.5. So I'm going to fill that in too, because then what I can do is get rid of this down the bottom. Gone. See you later. Okay, this looks good. Now, we're also told, given that the reaction at E is double the reaction at F. Okay, so wait, let's write that out. Reaction at E is equal to double the reaction at F. So this here. We've got to calculate the distance of the center of mass from C. Okay, so center of mass, again, we don't know where it is, right? So let's just put it somewhere. Where are we going to put it? Well, because the reaction at E is double the one at F, I think it's going to be quite close to E. So I'm just going to say it's over here. And we'll put 60 newtons coming downwards. That distance there is going to be X, because that's the one we're looking for, right? And I think we're ready. Let's go. Let's get cracking. So upwards equals downwards. So RE plus RF is equal to 60. Now we're told that RE is equal to 2RF. So we can say 2RF plus another RF is equal to 60. That means 3RF is equal to 60, and therefore RF is just equal to 20 newtons. So that one there's 20 newtons. And if we look at our formula at the top here, we've got RE is just 2 lots of RF, right? So that's just 2 times 20, which is equal to 40. Okay, good. So we've got 40 newtons over here. And this is great. So now we're just going to take moments to finish this off. We're going to take moments about C. Again, remember what I said last time, right? You can take moments about anywhere. So make sure after this, practice it. Yeah, don't be lazy. Go and practice taking moments from different points, okay? Because it's really useful. As I said, when you've got the spare time in your exam, go back, do the question again, but from different points, and make sure you get the same answer. Now, because it's resting horizontally, we're going to say clockwise moments are equal to anti-clockwise moments. So I'll put anti-clock again. Clockwise moments are going to be caused by, let's get a highlighter here, is going to be caused by this 60 newtons over here. So we can say 60 times by X. Anti-clockwise moments, though, are going to be caused by RE and RF. So for that there, we'll have 40 times by, well, 1, because that distance is just 1 there, plus, and that's 20 times by, well, that distance there is 2.5, wasn't it? So 2.5, there we go. So let's just simplify this down a tiny bit. We've got 60x is equal to 40 plus, what's this, 2.5 times 20, so we've got 50. That means 60x is equal to 90, and that means x is going to equal 9 over 6, or I guess we could say 3 over 2 slash 1.5 meters. There we go. So we know that this distance here, 1.5 meters over there. And if we just check out again, the length was originally 4 meters. And because the center of mass is at 1.5 meters, what we've just proved is obviously that this is a non-uniform beam. Fantastic. Now, different example this time, a little bit more tricky, but let's have a look and see if we can get through this. We've got another non-uniform rod of weight 50 newtons and length 5 meters. Is freely hinged to a vertical wall. So here's the hinge, right? Which means this thing here is the rod. So let me just write that out now. That there is your rod. And there's your hinge. So it's held in place by a cable attached from one end of the rod to the wall. Okay, so that tells me that this here is my cable. Okay, And this here, this must be the wall. So I'm going to put maybe WAL. There we go, wall over there. Now the cable is angled at 60 degrees to the rod. So let's fill that in as well. So 60 degrees over there. And then what are we told here? Given that there is a tension of 40 newtons in the cable. Okay, so what you need to realize is there's going to be tension in the cable. It's going to be tight. And what that means is the cable is pulling the rod in that direction. So towards the wall, right? So you fill that in there as 40 newtons. There we go. So you've got that. And what else? What else are we told? We need some more details here. I mean, the length of the rod was 5 meters. So I guess we could fill this in as 5 meters. But it's non-uniform again, so we don't know where the mass is, right? So maybe let's just pop that in somewhere. I'm just going to go here for now. Bang. And we'll say this here is 50 going downwards. Now, from my previous videos, I talked about hinges, right? And I said at a hinge, we're not really sure which way the forces are acting. It can act upwards, it can act sideways, who knows? But what we can do is be smart and take moments about this point, because if we take moments about this point, we don't need to consider the forces at this point. So we're going to do that when we get to it, not now, when we get to it. So first thing we've got to do is consider our, well, do we need upwards and downwards? No, I don't think we do actually, because we've just got this force going clockwise, and we've got this one going anti-clockwise. So actually, well, here we don't need upwards and downwards actually, so let's just go straight into it. And let's just go with clockwise moments are equal to anti-clockwise moments. So if we're thinking about our clockwise moments, that's going to be caused by the 50 newtons down here. Now, do we know the distance from the wall to the 50? No, we don't. So we'll call it x for now. So we can say that's 50 times by x for the clockwise moments. Now, anti-clockwise, we've got, well, this 40 newtons, right? But. This distance here, 5 meters, is not perpendicular to the 40 newtons. So this is no good. We can't use the 5 meters. So we need to do something else. What are we going to do? Well, we need to draw in the perpendicular distance to that 40 newtons. So I think, there we go, that there is going to be the perpendicular distance. So what we should do is draw this triangle out somewhere, maybe a bit smaller. Let's do it over here. So like this. And we've got that as 90 degrees. We know that this whole length is 5 meters along the bottom. And what are we trying to work out? We're trying to work out this length over here. We know that that angle is 60 degrees. So I think this is all good. We just got to label it. So x is going to be the opposite. This will be our hypotenuse. So we need to use the sine ratio. So sine 60 is equal to opposite, which is x, over hypotenuse, which is 5. And that means 5 sine 60 is going to equal our distance, x, over there. So look, let's add that to the diagram. That's 5 sine 60. Okay, now we're ready. So our anti-clockwise moment is going to be the force, that's 40, times by the perpendicular distance, which we just said is 5 sine 60. Okay, a bit of simplifying. So 50x is equal to, well, 40 times 5, that's 200 sine 60. Divide across by the 50, and that's just going to be 4 sine 60. Okay, just fire that into the calculator quickly. 4 sine 60, what does that equal? Let's just type that in. 4 sine 60. Bang. Oh, not in radians. Get out of radians mode, innit? Silly me. So we need to be in degrees. There we go. And that comes out as 3.46 meters. And that there is to 3 significant figures. So there we go. Nice and simple. So with that one there, just remember, we didn't actually need to take upwards and downwards forces because we already had just 2 forces on there. So it was easy. One was going anti-clockwise, one was going clockwise. Simple. Now, it's time for you to have a go. Now, here's one that involves some cables, right? But it's the same kind of principle. There's going to be tensions going upwards. So just remember that. Apart from that, it's still the same process, upwards, downwards, and then you need to go take moments, anti-clockwise equals clockwise, etc. So have a go, and I'll see you in a couple of seconds. Okay, let's roll. Now, we've got a non-uniform beam AB, so hopefully you labeled this as A, this is B. It's got a length of 7 meters, so the whole thing is 7. I'm just going to hold fire there for a second. And it's held horizontally in equilibrium by 2 vertical wires at A and C. So obviously this wire here is at A, and what the wire has, remember, is tension, right? So tension upwards, we'll call that tension at A, and then the other wire is at C. So we'll say this is C, and this here is going to be tension at C. And they told us that A to C is 6 meters. So I'm going to fill this in now. We're going to say this here is 6 meters. And remember, the total length of the rod was 7 meters. So we can say this here must be 1 meter. Okay, this is good. Now, we're also told that the tension in the cable at A is half the tension in the cable at C. So what they're telling us, the tension in A is half of the tension in the cable at C. So what we can say is tension in A must be equal to half of the tension in C, or we could say 2 lots of the tension in A is equal to the tension in C, whichever you want to put. So we'll have that in a box just over there. Now, the last thing we need to do on our diagram is fill in where we think the center of mass is going to be. So just pop that anywhere. I'm just going to say it's here for now, downwards, and that there's 30g. And the distance, we'll call that x. Okay, and I think we're ready to go again. So upwards equals downwards. So we've got TA, which is upwards, and TC, which is upwards, but downwards only 30g, so equals 30g. Now we can do some substitution. I'm going to use that one there. So TC is equal to 2 lots of TA. So TA plus 2 lots of TA is equal to 30 Gs. That means 3 lots of TA is equal to 30 G, and TA must therefore be 10 G. Now if we use that, what can we say? Well, we can say 2 lots of TA, so 2 lots of 10 G is equal to TC, and that means TC must be 20 G. So we can fill this in on our diagram. So we've got this one as 10 G and TC as 20 Gs. So that's that, done. And now all we need to do is take some moments to work out what the distance is. So I'm just going to take moments about A, right over there. So if we do that, let's go with moments about A. Clockwise, hopefully you can see, is going to be this 30G. So that's just 30GX is equal to, and 20G times by a distance of 6. So it's 20G times by 6. So we've got 30GX is equal to 120G. We'll get rid of those and then just divide that 30 across. And that's going to give us X as 4 meters. And there it is. So 4 meters. So it is somewhere around here. Maybe a little bit closer actually to that side. But we get the idea. So that's it. Hopefully you've got that question correct. If you have, you smashed it. You've made it to the end of the center of mass chapter. So well done. There's one more bit to go, I think, which is on tilting. So we'll have a look at tilting. Should be quite easy though, tilting, yeah, pretty simple. But yeah, check out those videos. They're coming out very shortly. In the meantime though, give us a like, subscribe if you've understood everything. And yeah, hopefully I'll catch you again in those tilting videos.